Welcome to the lecture titled Tuning of Reconfigurable PID Controllers. PID controllers are widely used in process control industries. Digital PID controllers are used in widespread particularly, but evolution of reconfigurable PID controllers has made a breakthrough in analog PID controller as it eliminates ADC and DAC requirements and reduces power consumption. What is ADC and DAC requirements? Since the process plants are analog in nature, you need to convert the analog signal to digital and digital signal to analog to operate the real time system which is analog in nature. Coming to the self tuned digital PID controller model, we see that for controlling the real time process which is analog in nature, we need to employ analog to digital converter, digital to analog converter, analog to digital converter and personal computer for controlling the analog real time plant. So, the digital PID controller or control technique requires one to employ a number of ADCs and DACs apart from a personal computer. Is it so when you are going to control the analog plant or analog system with the help of some analog PID controller? No, that is not so. Since the processor plant is analog, you do not require any ADC or DAC, rather an analog controller can be employed to control the dynamics of the process in a straightforward manner. Now, the relay is used here to identify the dynamics of the process. So, the model for or the structure for a self tuned analog PID controller can be given like this, which requires less gadgets or equipments or components compared to that of a digital PID controller. Now, we will see the hardware implementation of some real time PI, PD and PID controllers. How PI, PD and PID controllers can be employed or can be designed using simple electronic devices. Now, this is an op-amp, operational amplifier. So, we have got op-amps. Now, when an op-amp is connected in this fashion with a resistor in the input and resistance and capacitance or a resistor and capacitor connected in the feedback path, then the dynamics gives us a PI controller. How do you get that one? Given an op-amp, if the input resistance is R A and you have got R 1 and C 1 in the feedback path, and let the input be V I and the output be V O, then the ratio of the two in frequency domain will be minus of the impedance in the feedback path divided by the impedance in the forward path. So, minus of R 1 plus 1 upon C 1 S divided by R A, giving us minus R 1 upon R A minus 1 upon R A C 1 S. Now, how to get a PI controller? If I employ further at the output another amplifier which will give you unity gain with gain of minus 1, okay, like this, then the output you get will be plus R 1 plus 1 upon C 1 S divided by R A. Then you will get V 0 upon V I S H R 1 by R A plus 1 upon R A C 1 S, giving us K P plus K I by S as the parameters of the P I controller. So, this becomes a P I controller with K P equal to R 1 by R A and K I is equal to 1 upon R A C 1. So, K P is equal to R 1 by R A and K I is equal to 1 upon R A C 1. So, this is how you design a P I controller using op amp, resistors and capacitor. Okay. Now, similarly, a P D controller can be designed using op amp, 2 capacitors and 1 resistors. So, how you will get the transfer function for that one? The transfer function for that one, when this R A is substituted by a capacitor C 2 and of course, we have got R 1 C 1 over here. Now, the V O by V I S will be, V O is here, please keep in mind V O is here, not here, V O over V I will be equal to plus R 1 plus 1 upon C 1 S divided by 1 upon C 2 S, because the impedance of the capacitor is now 1 upon C 2 S in frequency domain. Then the subsequent expression will be R 1 plus 1 upon C 1 S times C 2 S is equal to R 1 C 2 S plus C 2 by C 1. Okay. And you get this as the P D parameters given as K P plus K D S, K P S plus K D, where K D, the parameter of the P D controller, K D is found from the ratio of the two capacitances C 2 upon C 1 and K P is equal to R 1 C 2. So, K P no R 1 C 2 S, K P is equal to, first you will get the K D S plus K P, sorry. So, K P will be equal to now K D is equal to R 1 C 2 and K P is equal to C 2 by C 1. So, this is what you have obtained, K D is equal to R 1 C 2 and K P is equal to C 2 upon C 1. So, it is very easy to implement in hardware the P I and P D controllers. Now, let us see how we can design a PID controller. It requires 3 op amps. This is the op amp you have got for summing the action of PI and PD controllers. So, where from you are getting the PID control action, this gives you the PD controller and this gives you an integral controller. So, this is an I controller. So, when you add the two, you get the PID controller. Okay. So, this is the summing, this is for summing the two signals and getting you the PID control action. How do you find again this transfer function for the PID controller? Is the same thing, you take the ratio of the two for PI. For this part, it will be simply your if the output is VO, if the input is VI, then VO upon VIS will be found as 1 upon C 1 S plus R 1 divided by 1 upon C 2 S plus, for this it will be 1 upon C S divided by R A. This is what you get. So, I will collect the terms now and write as VO by VIS is equal to R 1 C 2 S plus C 2 by C 1 plus 1 upon R A C S. So, this is what you get, from where when you compare or put it in the standard form, this is your derivative controller. So, K D S plus Kp plus Ki by S, giving us Kdh R1C2, Kdh R1C2, Kph C2 by C1 and Kih 1 upon RAC. Okay. So, this is how a PID controller is implemented in hardware using 3 op-amps and a number of capacitors and resistors. Now, interestingly, you see that any gain can be obtained from the ratio of 2 capacitors. Is it possible to replace the resistors by capacitors? What are problem with the resistors for us? When you are going to change the values of a PID controller, you need to change the values for resistors. How can you change the values for resistors without replacing them? Is it possible to change the values of the resistor by some command or without physically replacing the resistors particularly? The capacitors you can implement very easily. If you have got variable capacitor, easily you can, or if you have got a bank of capacitors, you can find various values of C1. How can? Either by the help of parallel or series combinations, it is possible to get various values for C1, but it is very difficult to get exact values for all the resistors you have in the circuit so easily. Is it possible to replace the resistors by some capacitors? If that is so, then our life will be very easy and we can reconfigure the PID controller or change the PID controller parameters very easily using software or using a computer. Okay. Now, a computer cannot be employed to change the R1 values particularly, R2 values particularly, RA values particularly. The computer can be employed to change the capacitances, capacitor values, whereas a computer cannot change the resistance values. Okay. So, if the resistors can be substituted by some capacitors, bank of capacitors or by some analog capacitor bank, then it is possible to have reconfigurable PID controller. What do we mean by reconfigurable? Which parameters can be controlled by software or by some computer. Okay. You need not again assemble or bring the resistor value and put, because it will take time, it will take much time to find accurate value for the resistors and substitute over here or put over connect over here. So, if it can be dynamically programmed by a computer and if the capacitors can be used to substitute the resistors, then it is possible to design a reconfigurable PID controller. So, the focus of this lecture is that how to design a reconfigurable PID controller. It has been found that recently the Anadim Corporation has introduced a device named as field programmable analog array in place of field programmable gate arrays. Field programmable gate arrays are used for designing digital PID controllers, whereas field programmable analog arrays can be used for designing analog reconfigurable controller. So, reconfigurable analog PI controller or PID controller or PD controller can be implemented using FPAA blocks or using FPAA. FPAA or field programmable analog array has got a number of configurable analog modules which can be easily accessed by a computer and can be configured by a computer, changed by a computer. Okay. Now, using this scheme, it is possible to design the real time systems. So, in this scheme, the control for a DC servo motor has been done using the FPAA controller FPAA kit. So, the FPAA kit can provide us reconfigurable analog PI controller. Also, the relay dynamics can be realized, implemented by the FPA. It is now connected through RS-232 with a personal computer, where the tuning formulae, the computation part of finding the PI controller parameters Kp and Ki will be done. So, Kp and Ki are found based on the plant model parameters. So, the DC servo motor dynamics will be identified first in terms of the K, theta and T, a first order plus transfer function model K, theta and T or T1. Then based on K, theta and T1, you design the PI controller parameters. So, these formula will be simulated or will be implemented in a computer. It is difficult to have computational facility in FPA, rather you can configuration facilities are there, you can reconfigure anything, but you may not be able to compute or find or estimate values. So, that will be taken care of by the personal computer. So, this is the photograph of an experimental setup we have in our lab, where we have used the FPA kit along with the signal conditioning circuit and various measuring test and measuring equipments, and this is the DC servo motor which is under control now. So, this experimental setup has been developed to see whether the FPA can be applied to retune the parameters of a PI controller, or to design a controller for a real time system such as DC servo motor. Now, I will talk about the advantages of FPA based controller over the DSP based, digital signal processors based controller. The power consumption of DSP halves every 18 months. This is one demerit it has. It is shown that using a reconfigurable analog array, that means FPAA, we can decrease power consumption by 5 orders of magnitude as compared to a DSP. So, the digital controllers are easy to implement, but they are subjected to cost because they consume more power. High performance data converters like such as analog to digital converter or digital to analog converters are required for a DSP based PID controller. Those are not required for FPAA based analog controller. The conversion speed, conversion precision and noise greatly affect the fidelity of the digital controller. That is not so in case of analog controllers. Further advantages of FPAA based controller are that the analog controller eliminates the need for converters particularly, which in turn result in saving of power, space and cost. You do not require analog to digital, digital to analog converters. Therefore, you save cost, you save space also, and you save power, because powers are consumed by the converters. As the power of the DSP is reduced, the power consumption of the data converter will dominate. Thus, their elimination is very advantageous. That would also be very useful for controllers used on which one? The FPAA based controllers can find use on especially on spaceships, where you have constraint on space. On mobile phones, size has to be small. Now, autonomous robots, because you have to have less number of ADCs and DSCs, and the cost will come down, or many similar applications. So, FPAA finds application particularly in spaceships, mobile phones, autonomous robots and many more applications. Now, how the FPAA is implemented, we will see. This is the basic block diagram of online tuning scheme for a PID controller using FPAA. Initially what is done? The switch 2 is closed, then the plant parameters are identified. When switch S2 is closed, then auto tuning test is carried out using of course FPAA. Okay. Then parameters of a first order plus dead time transfer function model are computed. Then the PID controller parameters are updated using the CAMS. What are CAMS? Configurable analog modules. Okay. This is how online tuning is done using FPAA. Now, what is that FPAA? Let us discuss a little bit about the device. This FPAA product of the company Anadim Corporation AN221E04 can be used for designing analog controllers. FPAA can be dynamically programmed using RS-232 and a computer, a PC. Variety of analog functions like amplification, summing, differentiation, integration, filtering can be implemented in it. Now, real time configuration of FPAA is also possible using dedicated software such as Anadim Designer 2. We have used this software for real time configuration of the PID controller and PIE controller in our lab. And this software runs with the help of C functions also. Now, design of PI or PID controllers can be done using the inbuilt analog functions. Okay. Now, this gives the basic structure of a PID controller as implemented in the Anadim's Anadim is AN will be there. So, AN221E04. So, you will have blocks like this in the FPAA kit, where the first block V1 collects reference inputs and the feedback signal. The signal is processed by the controller now. The controller is implemented in this fashion, and the controller passes on signal to another summing block, which ultimately gives you a reconfigurable PID controller. Now, different blocks have got different gains. The blocks are implemented with the help of gains. So, this is the output of the controller, not the final output of the controller. Now, the PID controller given in the standard form such as Kp times 1 plus 1 upon TIS plus TDS can be expressed as GCS is equal to Kp plus Ki upon S plus KDS, where look at carefully the way the gains are found now using the gains of the individual blocks we have here. How many blocks are there? There are 4 blocks, 1, 2, 3, 4. Each blocks have their own gains or constants that can be used. So, Kp is implemented as Kp is equal to G1 minus Gg3, Ki is equal to Kg2, Kd is equal to Gg3 upon Fc. What are G's? G1, G2, G3 are the gains of summer block 4. So, the summer block has got G1, G2 and G3, the gains like this. Okay? The summer block has gains like this. The K is the integrator constant in per microsecond. G is the gain of the differentiator block. So, the differentiator block has a gain of G, and Fc is the frequency of operation of the configurable analog modules. This frequency is very important for us, because unless this frequency is set accurately or properly, you will end up in trouble, and the real time implementation of FPGA will have some real difficulties. Now, how to choose the Fc and what are the effects of Fc, the frequency of operation of the analog modules or blocks. Fc plays an important role in deciding the gains of the PID controller. How that is so? The maximum values for G1, G2 and G3 are limited to 100. Therefore, in order to increase Kd, the derivative constant you have in the PID controller, Fc is chosen in such a way that G1 does not exceed 100. Okay. Otherwise, what happens if you look at this one, G is over Gg3 is equal to Kd Fc. Therefore, Kp can be written as G1 minus Kd Fc. So, if Fc is not chosen properly, then we may not get proper value of Kd, and we may get an ultimate value which is greater than G1, rendering a negative proportional gain of the PID controller. Then what will happen to the system? When you have got a negative gain of the PID controller, the controller will not act, rather you will develop an unstable closed loop control system. There is the demerit associated with the choice of Fc. So, please be careful in choosing Fc particularly, and proper care must be choosing Fc. Choose Fc in such a way that there will be no aliasing effect. So, when you process the signal, you will be subjected to aliasing effect that can be also overcome with proper choice of the Fc, the frequency of operation of the configurable analog modules or blocks. Okay. Now, I will go to a little bit of the FPGA configuration. This is the hysteresis we have assumed in our relay. This is the relay is implemented in the FPGA, and this is your PID controller implementation. So, we have the PID controller realized in this fashion, where this is the planned output is collected here through this port, and this output means this is not the plant output, this is not the plant output. Okay. Be careful, this is the output you are getting from the relay. So, relay output is basically collected and given or collected and given to proper point, okay, proper node. So, this is the real time implementation of a FPGA configuration having relay and controller. It is unless you go through and see the kit, it will be difficult for you to follow these symbols what are shown over here, different modules, but please keep in mind we have got a number of CAMs, configurable analog blocks in it. Okay. Now, I will come to again the block diagram of online tuning using FPGA. Having shown this, we will go through some flow chart that gives you the way the FPGA is used to design reconfigurable PID controllers. So, the flow chart for online tuning method is given over here. Initialize the gain margins and phase margins and necessary data. Where you do this data processing? This is done in the PC, in the personal computer. As you see, your system is connected with a computer which will compute the gains of the or parameters of the controller, configurable controller. Okay. Now, then run the relay with S1 open and S2 closed, that is without controller in the loop. Calculate the ultimate gain Ku and ultimate period Pu, and then calculate the PID parameters using Ziegler-Nichols formula. So, we have in the literature we have formula, many formula given by Ziegler-Nichols. So, use that one to find the PID parameters. Now, initialize the PID controller with new values, that means update, not initialize, it will be update the PID controller with new values in the FPGA. So, with certain commands it is possible to reconfigure the PID controller with the new values of new calculated values. Okay. Now, go to the decision block, check for any change in the output, particularly when this tuning will be initiated, the output will be tracked continuously. So, this is your output, system output. So, the output will be tracked continuously by the FPGA, and as and when the output increases or decreases above or below certain threshold value, then the auto tuning is invoked. Okay, the relay is invoked and then the auto tuning process starts and the updation of PID parameters are carried out till the output is acceptable to you. Okay. Now, check for any change in the output. If it is yes, close the relay switch, that means go for the auto tuning test and estimate the new critical points, calculate the new PID parameters and send it to FPGA. And if the output is within bounds, then do not go for any action, that means the FPGA will remain silent, okay, or the FPGA will not remain silent, updation of PID parameters will not take place when the output is within the tolerable limits or if the output is satisfactory. Okay. Now, I will describe now the results of two real time experimental setups. So, two plants were used to carry out tuning experiments. One plant was a permanent magnet DC motor PMDC, and the second one was realized by a process control simulator. Okay. So, thus we have got two plants or processes, a DC motor as process 1, whose dynamics was identified using the relay test H. GP1S is equal to 0.666 e to the power minus 0.05 s divided by 1 plus 0.335 s. So, the DC motor dynamics, the PMDC motor dynamics is represented by the identified model GP1S. Okay. So, we have obtained a first order plus dead time model for the real time system, a DC motor. The DC motor can be, the dynamics of a DC motor can be given by, obtained by this first order plus dead time transfer function model. Similarly, the process realized by the process control simulator was found to be giving a transfer function of the form GP2S is equal to e to the power minus 0.001 s divided by 1 plus 0.05 s. You please carefully observe the time constant values and the time delays. Those are very small values. And it is difficult to implement those values using op-amp and resistors, capacitors. So, use of FPGA enables us to design controllers, reconfigurable controllers for real time plants such as a DC motor and a one realized by a process control simulator. Now, the initial and final values of PID parameters are tabulated here in this table. For the DC motor, initial controller parameters are Kp is equal to 11.58, Ti is equal to 0.0185 and Td is equal to 0.0046. How do you find the initial controller parameters? Using the Ziegler-Nichols method. Okay. So, perform a relay test and obtain the initial controller parameters using the formula given by Ziegler and Nichols. Okay. Then make use of R tuning formula. We have discussed a number of PID, PIPD, PD, PI controller tuning formula. So, make use of R tuning formula and estimate the final controller after auto tuning, and those are found to be Kp, Ti and Tdh 8.195, 0.0808, 0.0194 respectively. Okay. So, we have found these PID parameters after conducting a relay test with the initial controller values given by Kp, Ti and Td as shown over here. Okay. So, the final controller is obtained after second stage of the relay auto tuning test. Similarly, the controller parameters for the process simulator are obtained and tabulated here. In order to avoid amplification of process noise, the measurement noise, large value of Td should be avoided. How can you avoid large values of Td? It can be scaled by a constant factor, say alpha. So, choose certain alpha value to scale down Td value, so that you can reduce the measurement noise during real time experiment auto tuning test and control. Now, what sort of output we did get? the final output when the reconfigurable PID controller was employed. The Ziegler-Nichols PID controller gives us the one shown by the black. Now, this has got a long settling time, but the method we have adopted with the choice of alpha equal to 2 results in PID parameters such that we have got a time response of this form given by the red one. Okay. Now, this time response is although subjected to a little bit of larger overshoot, the overall performance in terms of improvement in rise time and improvement in settling times are concerned, we have got superior performance compared to that given by the Ziegler-Nichols method. Okay. So, simulator has also given similar results. We have got improved performances, we have not made any comparison of results over here for different values of alphas of course. Now, the alpha chosen should be 2 as it shows you have, if you go for higher value of alpha also you have got steady state error. Okay. When alpha is 2 we get suitable time response from the closed loop system. Now, real time experiment of a DC motor servo motor is now carried out using a reconfigurable PI controller. In the second case, the hardware setup is shown over here. Okay. Then when it is also a relay test is performed to the sampling time, relay amplitudes and hysteresis settings of 16 milliseconds plus minus 0.17 volts and plus minus 20 millivolts respectively, we are able to find the initial controller settings as Kp is equal to 6.3662, Ki is equal to 0.55 with the help of Ziegler-Nichols formula. Of course, after obtaining the limit cycle parameters such as the critical gain and critical frequency. Now, following the online tuning identification method, the process dynamics was estimated as GPS is equal to 0.9937 e to the power minus 0.199 s divided by 1 plus 2.0926 s. So, this is the dynamics of a DC servo motor. That means, a real time system such as a DC servo motor can be described by this transfer function. So, whatever output you get from this transfer function will be the one you get from a real time DC servo motor when appropriate signal is applied. This is the transfer function model of the dynamics of a DC servo motor. Okay. Now, final controller settings are done as Kp is equal to 0.9445 and Ki is equal to 0.4391. Now, closed loop responses using the initial settings for position 90 and using the updated PI settings for the new position of 150 degree. What are these positions? I mean, we are having a DC servo motor and we are going to control the position of the shaft. So, for different reference values, we have got closed loop responses and those responses are shown in the figure. This is the time responses we get from DC servo position control system. Now, as you see, this is the normal operation. During the normal operation, we get the response. During the auto tuning test, we get the time response as this one, and when the position is changed from 90 degree to 150 degree, you see 150 degree, all these are in degrees. Okay. Then we get a time response of this form. Now, after some time intentionally we inject some disturbance, that means what? You change the shaft position and lift, then automatically the shaft will come back to the original position, and that is shown by this time response. So, given a load disturbance means change it, then you will leave it, automatically the shaft will come back to its original position. So, this shows that the developed control system can successfully reject static load disturbances. Okay. Tracking performance is clearly enhanced with almost no overshoot. See, if I look at this performance given by the updated PI controller, then there is no overshoot over here, no overshoot, whereas we have got quite satisfactory rise time and settling time. So, I can say we have got overall satisfactory performances given by the reconfigurable PI controller as far as controlling the position of shaft position of a DC servo motor is concerned. Okay. This is what we get the beauty of this technique, FPA based controller technique we have. Now, coming to another point, that we do get also reduced control efforts for obtaining the desired position. So, the control efforts have been not been shown here, that has been seen that in terms of utilization of power, in terms of use of hardware and in terms of space, and so we have got benefits. Okay. So, that way it is said that reduced control efforts are made for obtaining the desired position, which is now 150 degree from the initial position of 90 degree. Okay. So, we started with 90 degree, keep in mind, and we changed it to 150 degree, and thus we got a time response of this form. Okay. Now, I will go back to the hardware setup little bit. The hardware setup has got a personal computer. So, requirements for this FPA based reconfigurable controller are a personal computer, Anadim's FPAA kit, then you have got measurement equipments, then signal conditioning circuit. You have to develop a signal conditioning circuit, signal conditioning circuit. Then your sensor, obviously we have used, it is not visible clearly, a tacho generator. So, sensor, and of course, you have got some ICs. Okay. So, these are the basic requirements one needs, one has for implementing real time FPA based controller. I will come to the summary now. So, hardware based implementation of various controllers has been described. So, a PI, PD, PID controllers can be realized using op-amp, resistors and capacitors, but there are certain limitations, like it is very difficult to change the resistors value particularly, and that requires us to go for reconfigurable PI, PD and PID controllers. Tuning of a reconfigurable controller is presented in the lecture, and also real time experimental results are presented to show that it is not difficult to design FPAA based reconfigurable PID controllers. Why reconfigurable controllers? As you have seen, to shape power, space and cost. One can go for the use of FPGA based controller than the use of DSP based controllers. Are there any limitations of the online tuning schemes? Yes, one has to be very careful when you are doing real time experiments. Particularly, you need to carefully set the relay parameter. So, relay setting has to be done accurately, or I would say judiciously. Secondly, the choice of FC, choice of the frequency of operation of the analog modules. These are the two things you must take care of while designing a FPGA based reconfigurable PID controller. Thanks.